have done transient analysis. Today I am planning for DC analysis and parametric sweep. Okay, so and this will be done for inverter and also for the ring oscillator. We are going to design a ring oscillator today. Okay, and also we are going to study how to sweep different variables in a circuit. Okay, so first of all, yesterday some people asked some doubts actually. So why some peaks are coming and how it can be eliminated. Okay, so that information that so first I will solve. I will show you how to eliminate those things. Okay, so first of all, I'm opening my software Cadence Virtuoso. Okay, so here already I have created a folder. Okay, I think yesterday I explained that. Okay, how I created a project. So here CMOS test. Okay, that is the folder which I have created. So inside of that CMOS inverter is there. Okay, so here I'm going to start my Cadence Virtuoso from this particular folder. Okay, so for that, I'm just opening a terminal from this folder. Okay, and here I'm going to open Virtuoso. Okay, so for that the command is Virtuoso. Okay. So I have already explained how to set this library. Okay, so also where I have installed my technology file, that means 180 nanometer technology or 45 nanometer technology, that and all. Okay. Yeah. So when you will type Cadence Virtuoso in your terminal, so you will get this window first. Okay. So you have to open library manager first. Then only you can able to visible the the projects which you have done previously. Okay, I have created a project CMOS inverter. Okay, so inside of this yesterday we have created inverter folder. Inverter, see, this is actually one file which yesterday we have created. Okay, so this inverter, this is another one file. Okay, another one design, not exactly file, and this is a design. It will be saved in file only, but it is another design. Okay, so yesterday we have created this particular design. Okay, so I'm opening that. Yeah, it's opening now. See here, it's having 180 nanometer technology attached. So if you are attaching 45 nanometer, here it will show 45 nanometer technology. Okay, so now see here the model which we have designed yesterday. Okay, so here I'm going to remove this capacitor. Okay, I'm going to simulate. So I have for testing purpose I kept that. Okay. Okay, so now we are going to simulate this particular inverter without capacitor. Okay, so for simulating a circuit, so we have to go to launch and ADE. Okay, and here I will show you one more time how to set this simulation. Okay, for example, we are going to do a transient simulation. Okay, for that you're selecting which kind of simulation should be performed. For that, inside of in this analysis tab, you can select this choose. Okay, and here you can select on this tran. So you can give how much time this simulation should be performed. So for that, I'm giving 500 nanosecond. Okay, and apply and OK. Again, I have to select the output which should be plotted. Okay, for that, here, see, these are the options which are available. Okay, so I'm selecting this setup output. Okay, and from design, I'm selecting this input and output. Okay, and here I'm just giving apply and OK. Okay, and just coming to this ADE, here on play button is there. I'm just pressing on that. Okay, so that it will start to execute. Okay, so here we are getting the output, but this is like yesterday what we got. That means here actually the output having some peak. Okay, so now we have to remove this. Actually, someone asked how to remove this. Actually, this peak is generating due to the high frequency switching. Okay, so to eliminate this, we can connect a capacitor. Okay, now we can see that here on peak is present. Okay, so now we are going to eliminate that. Okay, so I will zoom that, and you can see that in a proper manner. Okay, so here a peak is available, so we are going to eliminate the peak. Okay, so for that we are going to place a capacitor. Okay, and one more thing, see here, when we will close this particular ADE tool, so it will ask to save. Actually, it is very useful to you. Okay, because if you are changing, if you are doing any modification on this circuit, and if you are going to execute, again, you no need to select the output. You have no need to set the transient settings and that. Okay, so for that, you can save this. Okay, so I'm saving into this state one. Any name you can use, you can select any different names also, you can select. Okay, so I'm just saving that. Okay, so next time I can easily open that, and I no need to select the outputs, and no need to set the simulation parameters or nothing again. Okay, so now I'm going to place a capacitor here. Okay, so the capacitor available on analog library, and inside of that CAP. Okay, cap. You can type cap, so that you can get capacitor. Okay, and here okay, default value will be 1 picofarad. Okay, you can use the same value. Okay, and you can place there, and using wire. So to create a wire, you can simply press W. Okay, you can just press W, so that it will form wire. Otherwise, you can use this. Okay, so just I have pressed the W button. Okay, and after that I am connecting here. So the this terminal should be on the ground. Okay, I selected. Okay, I connected like, and I'm checking this. Actually, this is a simple check only. This is actually DRC, design rule checker. So it will check only design errors in this particular circuit only. It is not like LVS kind of thing. It is simply, if any net is not connected, it will simply say that okay, there is not, that net is not connected. Okay, so like that, a simple check it will do. Okay, but you should perform the simple check, otherwise you can't simulate. Okay, it will show some error. So first you have to perform, you have to save this, and this is actually check and save. Okay, if any error or any net is not connected or something kind of like that, any small kind of errors is there, means it will indicate that. Okay, so first of all, I'm saving that. Okay, and going to launch ADE. And again, I no need to set, because previously I have saved that state. Okay, so I'm just opening that state, and see here state. I have selected and opened, so that it will be automatically saved. Okay, you no need to do that again and again. Okay, so now you have to simply do the simulation. Okay, see here the peak has been removed. See, okay. See, this is the input and this is the output. Okay, but actually this capacitor, it is using only if it is very necessary. But that small peak, actually it won't destroy the entire system. Or for example, if you are going to design an ADC, it won't make that much of effect. Okay, but actually some designs, actually that might make some problems. So at that situation, you're supposed to use a capacitor, and you show, yes, that's a filtering only. It is a simple technique only. That is a filter. It will, that capacitor will act as a filter. Okay, so it will be acting as a filter and it will remove. Okay, so this that peak actually it will make a more problem when we will go for latest technologies, like if you are going for a 45 nanometer technology, the peak will be more. Okay, and if you are going for again that technology, the recent technology, FinFET, carbon nanotube, so there and all you can find more peak. So that and all, by using this capacitor or while doing some filtering technique, you can eliminate. Okay, so this is actually the how to eliminate that peak. Okay, and now next we are going to design we are going to study the parametric sweep. Actually, yesterday I have not sorry, not parametric sweep, parametric sweep also I'm going to explain. Before that I'm going to explain the DC sweep. Okay, so inverter DC sweep I'm going to explain. Okay, so first of all, I'm going to make a circuit according that. So here actually we have connected a pulse generator, but actually pulse generator is not necessary here. Okay, to perform a DC sweep. Okay, so for that, what I'm going to do is, so I have already created the circuit, but if you need more experience, then we can create the circuit again. Okay, so I will show you how to create a circuit again, how to modify the same circuit. Okay, I need this particular circuit, but I'm going to create a new copy of the circuit. Okay, so what I'm doing is, first of all I'm going to create a new uh, file for this. Okay, so for that file and creating a new cell view. Okay, so here the cell view will come. So inverter DC sweep, I'm giving name like that, DC sweep. Okay, so again I'm that will be saved inside of the CMOS inverter library. So I'm going to create a new empty like this. Okay, so now what I'm going to do is I'm opening the previous design which I have done, inverter cap. Okay, so both will see. Now the thing is, in the same window you will get two. Okay, so you can swap this, or you can just by selecting this you can change the window. Okay, now I'm going to copy this. See, I'm selecting this. You understood, right? So just selecting the entire design like this. Okay, and simply pressing C. Okay, I'm going to copy this. Simply I'm going to, yeah, simply pressing C. I'm just copying this, and see, you can select here and you can place here. Okay, so now otherwise you have to start from the scratch. That means you have to go here and select transistors and DC voltage sources. Everything has to be selected. So that is already you have studied how to do that. That is not necessary here now again. So now what I'm going to do is I'm replacing this with a DC source. Okay, that will be used for a sweeping purpose. Okay, so now I will I'm going to delete that. Okay, and I'm going to place an DC source here. Okay, so simply moving that, copied and pasted. Just I made a copy of that, and I'm deleting that. Okay, and see, this will be connected with input. Okay, so I'm just modified. I have just added a DC source. Okay, and remaining circuit same. Now for better you can remove this. This is now, this capacitor is not necessary now here. So so that is not necessary. I have removed that, so that you got a simple inverter. Okay, this is a very simple basic inverter. Instead of pulse width generation, we have connected with a DC voltage source. Okay, now I am going to save this. Okay, I have saved, and I'm checking any errors. Okay, so check that, save and check, and launching ADE. And here I have to set the which kind of simulation or which kind of analysis I have to perform. Okay, so for that, see here, analysis, and choose. I am going to perform a DC analysis. Okay, so for that I'm selecting this. Okay, and here, see here, various options are available. Temperature you can sweep, design variable you can sweep, component parameter you can sweep, model parameter you can sweep. Okay, so now here we are going to sweep component parameter. Okay, so I'm selecting here component parameter and select component. Okay, so it will show when you will press that select component, it will comes to this particular window. Here you have to select which you are going to vary. Okay, so I'm clicking here this a DC source I am going to vary. Okay, I'm just clicking here, and which inside of DC, you know that DC voltage is their magnitude phase. So like that, there is a lot of options are available. So I'm selecting I need DC voltage should be varied. Okay, so I'm selecting that. I'm coming here. Okay, so that this window you can come, you can open, you can just select this window. See here, I have this name will be available here. So V0, in that you are varying the DC parameter, and here how much the value, so the starting and stopping. Okay, so how from which range you are going to vary. So I'm giving here 0 to 3.5. Okay, 3.5 I'm selecting. I'm just giving. So here the sweeping options are available: automatic sweep and linear sweep and logarithmic sweep. So automatic sweep means it will automatically defaultly by giving analyzing this range which we given. Based on that, it will create some steps. Okay, or some sample value it will be generate. It will generate. Linear means we can select, for example, we can how many, see here actually they are given step size. So step size 0.1, if we are giving first value will be 0, then 0.1, 0.2, 0.3, 0.4, like that it will be incremented. So number of steps means the total this particular 0 to 3.5 will be, for example, if I am giving 10, it will be divided with 10 steps. Okay, but in this case what I am feeling is automatic is best. So, but some cases, if you want to analyze a particular DC value, then you can use for this that one. That is anyway, anyone you can select. Okay. So, but actually for this, what I'm suggesting is automatic is best. We can keep it and apply, and you can give okay. So here the DC analysis came here, and you are going to select the output. Okay, so which output should be plotted. Okay, so again you are going to select that. So set up outputs, and from design you are selecting. So here input, and here output you are selecting, and okay, and you're going to uh, execute. Okay, so for that you are simulating. See here you got. Okay, yeah, here now the response you are getting. Okay, but here actually for an ideal, for a burst inverter, this particular this particular point should come around 1.6 or 1.8. In that range it should come, that would be burst. So here if you are checking, this is the input. Okay, so here we are giving, when we are giving input as low inputs, it will give high output. When we will give high input, it will give low output. Okay, so this is actually the DC parametric sweep. So if we want to change this, so for that also we can. So what will happen if the width will, if the width changes? So that are actually we are going to analyze now. Okay, so if the width varying, what will happen? Okay, so for that we can perform parametric sweep. Okay, so now what we did is actually DC sweep. Now we are going to perform parametric sweep. Okay, I will show you how to perform parametric sweep. Okay, So this is very important. You have to listen in a very proper manner. Then only you can understand. Okay. So now I am going to close the previous simulation settings and all. Yeah, I will save the state. Okay, it's saved. Now I'm going to change the width. Okay, so for that I'm selecting this PMOS, and already if you want to see the properties of this particular PMOS, you can press Q button, or you can right click and you can select this properties. Here the properties window will come. Yeah, see here, this is the properties. Okay, you can select the properties, and here the options will be there, the total width and length. Okay, this actually you can't change, this is a minimum. So now the width we are going to change. So for that I'm setting this width as a variable here. Okay, now actually yeah, one more thing before that. Normally for an inverter, for example, this width, so for PMOS the width is 2 micron, means the NMOS width should be uh, 1 micron. Okay, then only you will get exactly the proper that particular response in the middle of the input voltage. Okay, so for that I'm going to vary, we can vary the width of this NMOS. Okay, so I'm selecting this NMOS and going to the properties, and here I'm giving a variable here. So I'm just giving W underscore VAR. Any name you can select. Okay, just I am more convenient with this particular name, so that I given the same name. Okay, so this name, anything you can give based on your uh, mental that what based on your naming that you can give. Okay, you can give. So now I given W variable VAR. Okay, and I have uh, closed that window. So here you are getting, see here W is equal to W variable, but here the W and L value, that is fixed. Okay, now here I'm going to save this, and I'm going to check any errors present or not. Okay, so I have saved that. Okay, and here I'm going to launch ADA, and here I'm going to select the previous state. That is very important, otherwise I have to do everything from the beginning itself. Okay, I have selected this. Okay, now the design variable should be defined here. Okay, so for that you have to select the variable. For that, edit variable and copy from. So W variable, I think here you can see, I hope that you can see that W variable came here. So how much number of variables are available? Okay, so all the variables will be displayed here. Okay, so W variable, a default value I'm giving. So defaultly the value was I think 2 micron. So I'm going to giving 2 micron. Any value you can give, that is not a problem. Okay, 2 micron. So I have given 2 here. Okay, but that we will sweep actually, but defaultly we should give some value, right? So but we are going to sweep that. Yes, somebody asked, do we, okay, somebody previously I think asked some questions like, can you show us the voltage value at logic 1 and logic 0 in simulation window? Oh, okay, and somebody, okay, I will show you that later. And do we need to select all the variables once again, sir? Actually, that variable, see, I will show you what are the variables you are giving, but that we have given only variable name, but we have not given the variable value, right? So that variable value should be specified. For that, when you will go for the simulation, you have to give a default value, otherwise it will show the error. Okay, you are giving a variable, but that variable should have some initialization. And normally in the programming, C programming and MATLAB and all, we will declare a variable with a value, right? So like that, we should declare a value. We should initialize a value. We have declared there, we are initializing a value. Okay, so that only we are going to do here. So that here edit variable option is there. So here you have to give that. Okay, so now I given 2 micron. Okay, yeah, 2 micron being given. I'm giving okay. Okay, and see, simply you can just simulate now also by using 2 micron what will be the DC characteristics. See, the same characteristics value we are have same output we are getting what we got previously. Now see here, simply you can change. See here the variable, that variable value. Here also you can see the variable value. You can double click on that and you can use 1 micron. So here you can make 1 micron and you can make a, you can apply this and give OK. Okay, I will show you again. Double click on this design variable option, that is left side of this IDE window. Okay, so here you can select W variable and here 1 micron. Okay, so you can give any value. I given 1 micron now. Previously it was 2 micron. Now I given change to 1 micron and I'm executing the uh, simulation. Okay, so here see this is changed. It came to 1.6. Got it? Now we can, for multiple value, what will happen? Okay, so we can analyze actually when we will make an ADC or any very big complex circuit. So generally by using a derivation and finding a particular proper value will be really very difficult. Okay, so for that only here actually in this cadence and this one parametric sweep option is available. Okay, so that so we can assume some range actually. In between that range we can simulate and we can just sweep, not simulate actually, we can sweep the values so that we can get a very good the results. From that we can select which is good. Okay, we can get a number of output. From that we can select the value which is giving a very good output. Okay, so I will show you now how to perform parametric sweep along with the DC sweep now we are doing. Okay, so for that, see here, available. Okay, that you if you want to sweep you can sweep that, but if you are not giving any variable means also temperature will be there defaultly. So now we are going to vary this VAR. Okay, so that I have selected now. So from which range I am just selecting from 1 micron to micron means you have to give U. Okay, and 2 micron. Okay, total steps. So I'm giving 10 steps. Okay, and you can simply press on this green color icon. Okay, that is run simulation. See here, this is the output. Okay, so we have varied the W ratio, W. Okay, the exactly W by L ratio. We are changing the W so that W by L ratio also will be changed. Okay, see here, you can see for each color. So this is for 1 micron. This is for 1 micron, and this is 1.1, 1.2, and this is for the 2 micron. Okay, so how it is varying. Okay, for this, from this actually what I'm thinking is the 1 micron is best. Okay, so 1 micron is actually this one. This is actually best when compared to the other width values. Okay, so this is called as parametric sweep. And now in the next, so we are going to make a ring oscillator. So for that, in the ring oscillator, how the various frequency, so how the different frequency signals can be generated, that can be, I will explain you that how to generate that. Okay. So first of all, next, I hope that you understood this one. What is a parametric sweep and what is a DC sweep? Okay. So this two we have done here. And also next action we are going to make a ring oscillator. Okay, so I am going to save this design and okay. Okay, Okay, so now we are going to make a cell view for this. Okay, so inverter, now actually this is a circuit schematic level. Now we are going to make a cell view. Okay, for that again I'm going to create a new library, new file, actually new file or new design. Okay, so I'm coming to library manager and file, new cell view, and coming here I'm giving inverter cell new. Okay, so inverter cell new, any name you can give, no problem. Okay, okay, I'm just copying this part. Okay, see here, got it right? See, I will show you one more time how I did that. Inverter cell. Here file, new cell view. Okay, inverter cell new. Okay, see, it came here. This is the window from the previous window. Okay, I have selected this much. Okay, this much enough. I will show you. I will tell you why I have selected this much only. Okay, so I'm just pressing control C, not control C. Okay, I'm just selecting on this and coming to this window. Okay, this is actually inverter cell new. You can see here inverter cell new. Here I'm pasting. Okay, so got like this. Okay, now you have to give the port. Okay, so here the port option is available. Create a pin. Okay, so just to click on that, and here you can give. I'm giving just D in, data in, any name you can give. There is not uh, any condition. There is no condition for that. Okay, you can just see. Oh, sorry. One more thing I will tell you. So D underscore in I given the name, and here you have to select the port will be input or output. So here the port is actually input. So I have selected the input and hiding this and making here. Okay, again coming here and D out. Any name you can use, but you have to select here output. Okay, now hide and place here that pin, and you can press W. Simply you can press W button. Okay, and you can select this, and this port also can be selected, can be connected. Okay, so this two should be connected. Now this is a very simple inverter cell. Okay, now I'm going to save this. Okay, I'm checking any errors there or not. Okay, and I'm creating a cell view now. See, for that create, see here, this is a menu which is available, menu bar. From that you can select create and cell view. See here, cell view, from cell view. Okay, I will show you one more time. From create menu, cell view, from cell view. Got it? One more time I will show you. Create cell view, from cell view. Okay, now you can press OK, and here see what are the input you given. The name will come, it will come here. Okay, D in and D out. Now okay, see, it will come like this. Now if you want to make exactly the inverter that shape, you can just delete this and you can make it. Okay, it is a bit time consuming, even though I'm doing that. Okay, it would be something, it will be something interesting. Okay, so that, see, I'm just making like this. It's a line tool, you can draw that. See, this is a line tool. See, I'm just drawing like this. Okay, so simply like this. Okay, and this is a circle. Oh, before that you can just move this part name there and instant name. you can make here, and you can place a circle here. Okay, and this is the T out variable that you can just move here or somewhere else. So you can make like this. Okay. Yeah, that name will be, somebody asked whether the name will automatically come. So yeah, it actually, the name will, what name you are giving, it will automatically come there. Okay. So here I given like that. I have just moved that and just moving that so that it will look good. It will look good. Okay. So now I'm saving that. Okay. Again saving and same thing. Okay. So now it is saved. I'm going to test this particular inverter cell. Okay. Got it? So now I have created an inverter cell. Okay, now I am going to test this particular inverter cell. Okay, so for that, I am again creating a new cell view from the library, new cell view. So I have to test that inverter, whether it is working or not. Okay, otherwise you can simply start with a ring oscillator. Surely it will work. It is 100%. You can check on this ring oscillator file itself. Okay, so I'm making ring oscillator OSC. Okay, I'm giving okay. Okay, already the file is available. I'm giving ring oscillator new. Ring oscillator new. Yeah. Okay, so now I'm giving this on. Okay, creating a new instant. I'm placing that particular new cell view which we have created in this ring oscillator. So it is available inside of this CMOS inverter live, and see the cell new. Okay, see here. I will tell you. I will explain you how to do that. See here, inside of the CMOS inverter library, you can select inverter cell new. Okay, that is actually newly generated cell, and that symbol format we are taking and we are placing here. Okay, yeah. Now we are going to test. We are perform. We are going to perform simple test on this. Just a timing analysis we are doing. So already I think we have a timing. See, from the previous, I have just opened the previous design. From here, I'm just copying the voltage sources, because actually why I am doing this is we are not having a lot of time. We have to finish by time. So that's why I'm doing like this, simply copying and pasting there. Okay. So I'm just copied and pasted here and connecting that. Okay. And here, this is the output terminal. Okay. And you can give the name here now. So D in or any name. So here D in and here D out. I hope that you understood that. So in a single click itself, I given the two names so that it will come. You can, by a single click itself, you can access that particular two names. Okay. So now we are going to check. Okay. So it's okay, saved. Now we are going to check now, check and save. Okay, so now it will show as minor error. Actually it is not error, actually it is warning. Okay, because here this is it is not connected anywhere, that's why it is showing, but it is not a problem, it won't make a much issue. But to avoid that particular warnings, in library itself on terminator is available. Okay, so that you can simply place that, but if you are placing a terminator, it will not show the error. Okay, but actually I forgot where it is, so that I'm not having time to search and take that. It is not a problem now. Now I'm going to save. Okay, this is not a problem, and I'm going to simulate that. So here, analysis, choose. I'm going to perform transient analysis, 500 nanosecond, and here I'm going to select the input and output, D in and D out. Okay, so here I have selected that, apply and okay. So here the variables came. I'm going to perform the simulation. So here I think we have to specify. Sorry, actually the problem is that the problem is inside of this actually we have specified W variable. I think W variable. Yeah, that variable we should just we have to specify that. That's only. Okay, we have to specify the variable. I forgot to specify the variable, so that's why that here. Okay, okay, no problem. So now again launching, and here the previously I have saved the state again state, so that I no need to um, do that again and all that DC analysis and all, selecting those and all, no need to do again. And here edit variable, yeah, here see this copy from it came. Okay, so that is nothing. We have simulated this particular. We have tested this particular ring oscillator. Okay, so this we have simulated now. Okay, it is working fine. Okay, again I will show you if you want one more time. Blanch here ADE, and I have saved the previous state. Okay, so there is a design variable that I have selected and just executed, so that that is running fine, no problem. There is no problem. Correct. Okay, yeah. Now we are going to make a ring oscillator. So we are going to cascade the inverters and we are going to make the inverter. Okay, so now I'm going to connect one more inverter, just pressing control and pasting here and here. Okay, So connecting this using a wire, and here to wire. Okay, and here one capacitor will come normally for a ring oscillator. Okay, so that capacitor is available inside of analog library, and capacitor. So default value we can keep now. Okay, so here we are going to place a capacitor in the output of each and every inverters. So here again, and connecting that by pressing W wire. Okay, and here connecting this again, and copying a ground by pressing C. I have just selected the ground button and I'm placing here. Yeah, placing here, and one more is needed. That is here. Connecting that. Okay, now this is not ring oscillator. This is just we have connected the inverters together. Okay, so now you can just give a names in between that each and every wires. See here W1 I typed, and W2 space W3, and giving hide, and see W1, W2 and W3. Okay, now we can simply simulate this. Okay, whether is it working fine or not. Okay, now I am going to simulate this. Okay, and selecting previously stored that states, and here from design I am selecting these variables W1, W2 and W3. Okay, and giving okay. This DOT is now not exist, so I'm going to delete that. Okay, and here, yeah, this 3 came, and now I'm going to execute and checking whether this particular 3 inverters are working fine or not. Yeah, it's working fine. We have connected capacitors, that's why the smooth output is coming. Okay, so now we are going to make a ring oscillator. So the ring oscillator, now actually this particular waveform we are getting through the pulse width generation. Okay, now ring oscillator means we are pulse frequency signal itself we are going to generate. So for that, pulse width generation module is not required. Okay, input is not required, so we are going to feedback. Okay, so here we are going to feedback. So I will show you how to feedback. DCC, it is necessary because we have to power the transistors. CMOS, we have to power the CMOS. So that is necessary. Now this is not required. We are going to delete. To delete a wire, simply you can press delete button so that this icon will come, and you can delete. Okay, now I am going to feedback. For that I am just pressing W and connecting like this. Okay, so this wire will be connected to the output. Got it? This is very important. Okay, now we are going to simulate. Open, selecting state, and selecting the all the outputs are selected, so no need to do anything. But D in is not existing now, so I'm going to delete because D in is now connected with the W3, so that that particular net is not exist now. So I'm going to delete that. So I'm going to remove that. And here one important thing, you have to specify the first, otherwise we can simulate and we can check what will happen. After that I will show you. Yeah, see here actually output will not generate because to do the simulation we have to set an initial condition. Okay, so that initial condition we should set. Okay, so I will show you how to set the initial condition for the feedback. Okay, this is a feedback. So for that feedback, how to set the initial condition. Okay, so for that you can select on simulation. Okay, and convergence aids and initial condition. Okay, so here 0 is available. We have to set that initial this particular feedback feedback wire is 0. So I have selected 0. Already defaultly 0 was there, and I'm just selecting this particular wire. So the wire name is actually wire color is changed. That means it is assigned to that particular wire with initial value of 0. That is very important. Otherwise, we will not get the output. Okay, giving OK, and coming to the simulator, you can just close this, and you can execute this. Yeah, I will show you that condition one more time. So somebody asked, but actually in my system, sometimes this error is occurring. I don't know why. I will check it. Okay, just a minute. Here. See here, the output is coming now. I will show you how to do that. Okay. Preeti John, she have asked actually how to do that initial condition. I will tell you how to set that. See here, output is actually generated. See, this is the waveform which is generated. Okay. So this is the final output. Okay. This is actually the final output which we have generated. Okay. This is a generated waveform. Now, if you want to get some more zoomed output, that means some more detailed information of the waveform, you can reduce the simulation time. Okay, so I'm giving here for something around 100 nanosecond. Okay, 100 nano. So giving apply and okay, and doing the simulation. See here, this is the output. Okay, so this is the waveform. Okay, now I will finish one more this one. That means a parametric sweep. After that, I will come to this. That is the doubt for that Preeti John. Okay, so how to set the initial condition, I will come after later. Okay, after that, after this parametric sweep. So I will tell you how to perform the parametric sweep. So for that, you have to set the variable. Okay, parametric sweep in the sense that always you are going to sweep a parameter. Okay, so for that you set a variable. So now here in this ring oscillator, we are going to sweep capacitor value. Okay, so that we are trying to generate a different frequency signal. Okay, so now I'm going to assign a variable here. Okay, so here I'm giving c underscore var, any name you can give based on your wish. Okay, I'm given c var. Okay, I'm giving apply. Okay, and here also by pressing q value or q key, I'm getting the properties. I'm placing that variable name there, and again for the third one, and one more very important thing is, see, you have to connect always odd number of inverters. I think you know that, right? Then only you will get the waveform. Otherwise, you will not get the waveform. That is very important thing. Okay. Now, yeah, we have given the name like this. Okay, variable name. I'm just saving this and opening this ADE and opening the previously stored state, so that I no need to select that parameter, that is transient analysis option and all, and selecting the variable, and here copy from C variable. Already for W variable we have selected. For C variable I am giving default value 1 picosecond. Okay, and apply. Okay. Okay. Now I am going to perform simulation. First we are going to perform simple simulation. Okay, output is coming correct. Yeah. Now we are changing the capacitor. Okay, so for that, to avoid the confusion, I am just placing only the final output. Okay, so this output, remaining outputs I am going to remove, so it will confuse. Okay, so I'm placing only the final output and doing the parametric sweep. So parametric analysis, I think you know that, right? Parametric analysis in the tools, first option, parametric analysis. Okay, and here you have to select the variable which you are going to sweep. So I'm going to sweep the C variable, capacitor. Okay, C var. So I'm varying from 1 picosecond, picofarad, capacitor, picofarad to something around 10 picofarad, or you can make 100 also, no problem. 100 picofarad, and total steps I'm giving 10 steps. That means 1 11, I think so, like that it will increment. Okay, so I'm performing the parametric sweep now. So total 10 steps. I'm doing the parametric sweep. It's going to simulate. See, this is the output. Okay, for various that is a different capacitor values. Okay, here. Yeah, see here, for 1 picofarad, 1.6, because we have given like that. This is for 100 picofarad. That means when the capacitor value what increases, I think. Okay, for 1 picofarad, actually what will happen, the frequency of the signal is, see, this is the frequency is more for 1 picofarad. For 100 picofarad, that is capacitance value more, actually the frequency is less. Okay, it is inversely proportional. See here, the frequency. So if you want, we can do one thing, we can change the capacitor value from 1 to 10 picofarad. Okay, so that you can get some more idea. Okay, that frequency waveform will come to the entire window. Okay. Yeah, see, it is some more clear now. Okay, see here, see, this is a waveform. Okay, so for 1 picofarad, 2 picofarad, 3 picofarad, 4, 5, up to 10. Okay, so this when the capacitance value is increasing, frequency is decreasing. Okay, so where actually this is using, actually this ring oscillator, this is actually, this particular ring oscillator can be converted into VCO, voltage controlled oscillator. Okay, where that VCO is using, actually that is using inside of ADC, and there is a lot of mixer. So there is the PL. So there and all VCO is using, actually. So this particular circuit, that means this ring oscillator, can be modified into VCO. Okay, by varying the capacity, by connecting some this one CMOS circuits here. Okay, we can vary the capacitor so that it can act as the VCO, voltage controlled oscillator, that can be used in ADC and PLL. So many applications, mixers, and there is a lot of applications are available. Okay, now I'm again coming to the that initial condition, how to set the initial condition. That point I'm coming. See, for setting the initial condition, you can come to this particular ADE window, and here simulation option is there, right? Simulation option. Here, inside of the simulation option, convergence aids and initial condition. Okay. So this already I have set so that it is, see here showing already I have set 0. So here it is showing 0. So what you have to do is simply you just consider it will be like this only initially. Okay, it will be like this. Okay, so you just make 0 here and you place here this particular location and simply select this particular node. Got it? So that it will assign that particular initial value to that particular node. Okay, and give OK. That's all. So if you are not setting initial conditions 100% that it will not execute. Okay, so that is a thing. So what we have discussed. Okay, so today what we have discussed is how to perform the DC sweep and how to perform the parametric sweep. Okay, and how to make a particular transistor or circuit into cell view, and how to design a ring oscillator, and how to how to set the initial condition, and how to sweep the capacitor value of the ring oscillator. Okay, yeah. So this is the thing we have covered. Thank you. I hope that you got some useful information about the cadence and also in backend design. Okay. If you have any doubts, you can ask. I think previously someone asked regarding the something logics. Can you show us the voltage values at logic 0 and logic 1 in simulation window? That if you want, I will show you that. I think that after placing the capacitor, we have done. So inverter cap. So I'm opening that. Yeah, this is the voltage. This is the input and this is the output. Yeah, I think Hemalata, she asked some doubt. For every time we have to set the initial condition. No, actually every time we no need to we no need to set. So once you set, after that, if you are saving that particular state, then again and again you no need to set the initial condition again and again. Okay, that is not necessary. Only one time if you are setting, that is enough. So like this, you can set for the multiple. If your design having multiple feedback, then for the multiple feedback also you can set. And if you are saving that particular state once, then you no need to set. If you are modifying means in the circuit means you have to set it again. Otherwise, you no need to set it again and again. Once you are setting, that is enough. Yeah. Somebody asked some doubt. I saw now only. It was interesting. I'm happy to be part of this. Thank you once again. Okay. How to do the power analysis? Yeah, power analysis. I will show you. So it can be done. See here, you can go to this ADE window first, okay, and you can select on this tools. Actually, in tools result browser, okay. So when you will click that, it will come to this waveform window. So here you can get the transient output, tran out, and inside of that, actually, this is a different voltage source which consumes how much power you can get. See here, see V0 took how much power and V1 took how much power. See here, this is actually in watts. It will come to microwatts, or you can convert to nanowatts also. So here you can get the power. Got it? So again, if you want one more time, I will show you. You come to this ADE, okay, ADEL tool, okay, and you come to this tool, tools, results browser, so that it will come to this window. From here, you can click on this tran output. This is a transient output only, okay, and each and every voltage source you can select, okay. So normally the power will be consumed from voltage source. That's why normally the main voltage sources you can select. So you can measure how much power it will take, how much maximum current, how much it will consume, and how much voltage, that information. Prakash, yeah, you can ask the question.
Hello, sir. I'm
Yeah.
Prakash.
Yeah.
Sir, we have designed a circuit in CMOS technology.
Okay.
Okay. For what purpose in PMOS and NMOS, the W by L ratio given it as 2, and as well as the NMOS technology 3 by 4th of the PMOS.
Yeah, that is actually that is based
If may,
on the.
I will change it out NMOS for 2 and PMOS for 3 by 4th of the ratio of NMOS. Is it
Yeah,
possible?
actually, yeah, in this design, actually, I have changed for the NMOS. Actually, I have selected 1/2. Half
Yes.
of that width, okay. So that you can change, actually you can, but if for the half ratio you can get better performance. But some applications and all, you have to vary. For example, that threshold vary. If you are going to vary for 0.5 volt or 0.75 volt, like that, if you want to
Yeah, yes,
vary,
yes, yes.
then you can vary that. But for an inverter, normally what we will do, we will just split the total voltage range into half, right? So below 0.5 means it should goes to or the output should be 1, or otherwise it should be 0. So like that we have to set, right?
But it is not mandatory.
Only inverter normally for inverter, for getting better performance, this is a condition.
Yeah, okay.
Got it?
But
What I'm telling?
yeah, yes, sir. But before the technologies, NMOS only we have to use that circuit means how it will be vary of CMOS and NMOS. The output
Normally
difference.
the default.
Yeah.
Yeah, output will vary actually. That a threshold, when the threshold will vary, automatically the output also will vary. But based on our requirement, we can make it. But when you will take a PMOS and NMOS from this particular this one cadence virtuoso, they have given for NMOS and PMOS they given equal value only.
Yeah. Okay, sir.
Got
Thank
it?
you. We have one more question. In
Yeah.
main
Tell.
parameters of VLSI design, area, power, and
Mm-hmm.
delay. Yeah, right. These three
Yeah.
parameters in a circuit maybe the reduced by.
Performance, that is actually
Yeah.
performance
Yeah.
normally
Yeah.
for a VLSI design. So we are developing a circuit means it should consume less power, it should consume it will take very less area, it should be portable. Okay. And another one is speed. Actually, based on the delay should be less, so that we can operate the device with high frequency, so the speed of the device should be more. So this three will be the main performance evaluation for the VLSI circuit.
Sir, okay. In a particular circuit, I
Yeah.
may consider these three parameters will be reduced, or otherwise may two parameters only considerable. If the circuit I have a designed, okay, sir. If
That's
may,
right.
I will consider as
Yeah.
a three parameters:
Tell me.
area,
Tell me.
power, delay. Those three parameters will be reduced, or otherwise any two parameters: area, power, or otherwise delay,
That
power.
is anything, any one. If you are, for example, you are going to develop an for fast FFT, you know, hear about, right, FFT, fast Fourier
Yeah, yeah.
transform.
Yes, yes, yeah.
So when compared to the previous design, if you are
Yeah.
reducing a power value, only power value, if you can reduce, that is a very good advantage only.
Yes,
Got it?
sir. Yeah, yeah. Main parameters will be an area, power, delay, na. So I have to
Area
answer
power.
that.
Any one, if you are reducing, that is good. That is not a problem. For example, if you are reducing power little bit reduced, but area little bit more means no problem. But the area should not be double or triple. Got it? So area some 1% or 2% improving, it is not a matter. But you can keep this to constant. Area and power you can make constant, and you can reduce the delay. Okay. So like that you can consider any one performance.
Yeah, okay, sir. Thank you.
Yeah. Welcome.
Sir,
Hello. Yeah.
sir, I have one doubt. So how to measure the
Yeah.
power using Verilog coding alone?
From Verilog code.
So we can, yes, sir. For a circuit, we can write the coding, right? So using that code alone, how to measure the power using this tool?
Actually, I think your voice is a bit distorting. So can you just make some distance between your mic and yeah? Can you ask now? Can you ask now?
Is it clear, sir? Is it clear?
Yeah. Okay.
Is it clear now?
Yeah.
Sir, for a circuit, we can write Verilog code,
Correct. So from
right?
Verilog code, you want to find out the power, right?
The,
Power, area, and delay, right?
yes, sir.
Yeah. Actually, for
Can,
that, RTL compiler on software is available. But if you want, I can show that I have in my system RTL compiler, Cadence RTL compiler. By using that, which you
okay.
have to decide which technology you want to use. For example, 190 nanometer means you have to decide the 190. You have to load the 190 nanometer technology. Then you have to synthesize your code into RTL compiler. After that, you can measure the area, power, and delay. Actually, that is a different
Okay.
software. That is called as RTL compiler.
Okay, sir. Which one
RTL
will give better result? Which one give better result using Verilog code or if we design a circuit?
Actually, Verilog code means actually if you are going for a very big design like a Fourier transformation or any compression techniques and all, so then you should use Verilog code only. There is no other way. From circuit level implementation is practically not possible.
Yes, sir.
Okay,
Yes,
so
sir.
based on the application, if you are going to make a small like a ADC kind of thing and purely back end design means you can use a transistor based design. For that, you can make the design in Cadence Virtuoso. Okay,
Yes,
otherwise you can
yes.
go with this one Cadence
RT.
RTL compiler
RT.
and encounter and all. Okay, so that is
Okay.
based on your application. So based on your design, it will measure the power. It is not based on the tool. So how we are making the algorithm, based on that, it will consumes the power.
Sir, can you show that, sir, how to measure the power using RTL, if
Yeah,
time permits?
yeah, just a minute.
Okay.
See, this is actually one sample code, one simple application. Okay, this is for a, can you see the window?
Yes, sir, yes.
See, this is a very low code for a crosstalk actually. That is a different block. Okay, so
Okay,
for that,
okay.
I am compiling this in 180 nanometer technology. Okay, so
Yes.
this is the RTL generator. From this report option, see from this menu, report, power, detailed power report, so that you can get the power report here. See here.
Okay, okay. Thank you, sir. Thank you, sir.
Yeah, yeah.
Sir, how to find the energy dissipation, sir?
Energy dissipation, I have to check. I never used or worked on that. Okay. Power,
Okay.
I think power consumption only available, but I have to check it. Okay. I never worked on that. I will check it. I will check it. I will update you. Okay. If I'm getting any information, I will update you.
Okay, sir. Sir, how to check whether the transistor is in active region or saturation region, sir?
For that, you have to perform the simulation. Separately, DC analysis will be there for each and every transistor. If you want to make separate study, you can simulate. You can take each and every transistor separately, and you can make the simulation. For that, better actually CMOS EDU on website is there. There actually their detailed information is available.
CMOS EDU.
CMOS EDU that I will type in the chat. So in there actually a lot of very good information available. Separately, you can take a transistor and you can vary the DC. That is your DC characteristics you can study.
That's
Okay, from that you can find out the active region and the bias condition, everything you can get. Okay.
Okay, sir. Thank you, sir.
Yeah.
Can you wind up, sir?
Yeah, ma'am. Yeah.
Okay.
Yeah, and one more thing. Hello, ma'am.
Then,
Hello.
yes, sir.
Yeah, ma'am.
Tell me, sir.
Yeah, ma'am. One more. Actually, some link is available for a tutorial. I will share that also. Okay, and I will put in the chat.
Okay, sir. Okay.
Just a minute.
Okay.
So some YouTube link I'm putting now. The same tutorial which I have done, it is done in CAD and this one Synopsys too. Okay, so that link also I'm keeping, and ring oscillator, parametric sweep. So this two link actually I kept in the chat. Okay, so you can use that to study the CAD this one for Synopsys tool also. Okay. Yeah.
Okay. Thank you, sir.
Yeah, you can wind up now.
Okay. Then, good morning, everyone. It is my privilege and pleasure to propose vote of thanks on this occasion. On behalf of Department of Electronics and Communication Engineering, I render my sincere thanks to our management, executive director, and principal for providing encouragement and support. On behalf of the Ramakrishnan College of Technology and Department of Electronics and Communication Engineering, I would like to extend a special thanks to our resource person, Mr. B. Deepesh, for accepting our request and spend his valuable time with us. Really, this today's session will be very much useful for those who are doing research in the area of VLSI. Thank you very much, sir.
Yeah, ma'am. Welcome, ma'am.
Thank you, sir. I also express my gratitude to our head of department, Professor Said Akbar, for giving an opportunity to organize this event. Also, I would like to extend my thanks to Mr. Jones Prasad Christidas, Assistant HOD, and Mrs. Tiba, Coordinator of this webinar, EC Department, for extending their full support. My appreciation and a very big thanks to all the participants for your active participation in this event. Once again, thanks to each and everyone. Thank you.
Thank you,
For,
ma'am.
for more information, participants can receive a e-certificate once you submit the feedback. The feedback form will be available in the evening. Thank you. Another information, Teepa?
Nothing, ma'am.
Hello?
Nothing, ma'am.
Okay, thank you.
Feedback link will be sent by tomorrow morning 10 a.m., ma'am. Participants, dear
Okay,
participants,
fine.
feedback link will be sent by tomorrow 10 a.m. You can fill the feedback link and get the participation certificate from them. So we are waiting for the approval to release the certificates. That's it, ma'am.
Okay, thank you. Thank you.
Once again, I will send the attendance link. You please be in a line, or otherwise I can post in the WhatsApp group.
Okay, thank you so much.
Thank you, ma'am. Thank you. Sir, thank you, sir. Thank you, sir.
Yeah, ma'am.